So, good morning, students. Today we are going to discuss about the topic Blasius solution for flow over a flat plate. Okay, so we already discussed about how the boundary layer formation happens over the flat plate. Also, we explained or we have gone through the topic the formation of boundary layer within a circular duct, and that is an internal flow. Here, flow over a flat plate is an external flow, external viscous flow. So we are going to discuss about the basic solutions. Okay. So while explaining or discussing about the boundary layer, we have discussed about the formation, what is the reason for the formation of boundary layer, then what is boundary layer thickness, velocity gradient, shear stress, and different flow regimes, laminar, turbulent, at the same time transition. Okay. So here you can see a flat plate with a flow over a flat plate, sorry, the formation of boundary layer over the flat plate. So here, yes, here you can see the things where you can see the velocity profile, and there is a transition which shows the arrow, which represents the mixing, and then you can see the turbulent portion here. So there is an expression which explains the PSF formation over the surface because of the boundary layer formation or velocity gradient, where mu is the dynamic viscosity of the fluid and du by dy is the velocity gradient or rate of shear strain. Now, how they are defining the boundary layer? The boundary layer is the region of flat of flow that develops from the leading edge of a plate in which the effects of viscosity are observed. So here, this blue color shaded region only where the viscosity effect will be significant or prominent or dominant. Outside the region, flow will be there, but viscous effect will be negligible because all the layers are flowing at same speed. Here, within the boundary layer, because of the no-slip condition on the surface of the flat surface, the gradient will happen, velocity gradient will happen, and as a result, viscous effect will be prominent. Shear stress will be developed. Okay. So outside the boundary of the boundary layer is usually given as the point where the velocity of flow is 99% of the free stream value. So till what extent the boundary layer will be available or will can be experienced. So that is what we explained here. So till the point where the velocity becomes 99% of the free stream velocity. Till that point, the boundary layer effect will be considered. Next is different flow regimes and at what value of Reynolds number the flow becomes transition or flow becomes bound, turbulent or flow remains as laminar. So that is what we are explaining in this particular slide. So laminar flow will be there, transition flow will be there, turbulent flow will be there. So in the initial state it will be laminar, flow will be very smooth, very orderly, happening one above the other layer will flow very smoothly. But slowly, once we move further or away from the leading edge, then the flow slowly becomes a little bit wavy or mixing will happen. Then further, it will become more turbulent towards the end. So different profiles we can experience within the laminar and within the turbulent region. So here they are explaining at what value of Reynolds number the flow becomes turbulent. So that is 5 into 10 power value. Okay, that depends upon what trace velocity, distance from the leading edge, and uh, dynamic viscosity or kinematic viscosity. Accordingly, the flow difference will be value or different. Value will be different. The formula will be different. Okay. So for most analytical purposes, critical number for the transition is equal to not find it and five. Right? From that onwards, the flow will be turbulent. Next is the relative shape of the velocity profiles in the laminar and turbulent flow. You can see here a flat plate and flow is happening. This is the free stream velocity V naught. So initially it will be laminar, then transition region, then turbulent region. How the velocity profile within the laminar boundary layer and how the velocity profile within the turbulent boundary layer. That is what we are explaining in this particular slide. So within the laminar boundary layer, the profile will be what the profile will be parabolic in nature, but in here within the laminar, sorry, turbulent boundary layer, the profile will be logarithmic in nature, and very near to the solid surface, there are subdivisions of the layers, which we can call as viscous sublayer, very close to the wall, then buffer layer will come, then overlap layer. So within the viscous sublayer, the velocity profile will be nearly linear, and towards the mainstream turbulent flow, it will be logarithmic in nature, and within the laminar regime, within the boundary layer, the velocity profile will be parabolic in nature. Okay, so that is what they are explaining. And structure of the boundary layer, laminar sublayer that is nearly linear, and turbulent portion which is relatively flat in comparison with the laminar profile. Next, you can see how the thickness is defined. The boundary layer thickness is defined, and at what point, till what point we will say that the boundary layer effect is dominant. So you can see here the fluid is coming from here only the turbulent or sorry the flat plate leading edge will start. Till then you can see there are straight lines coming, and once it reaches the flat plate, it slowly it will start. Uh, but moving forward because of the effect of viscosity. And here they are explaining at 99 meter per second. So at the what velocity flow is coming? 100 meter per second. So at what will be the velocity over the line? 99 meter per second, 99 meter per second, 99 meter per second, 99 meter. But free stream it is above 99 meter per second. Okay, that is what they are explaining. How they are defining? So till the point where velocity will be 99 percentage of the free stream velocity. That till that region, boundary layer effect will be prominent or can be considered. So here again, they are explaining over the flat plate laminar will be till 3 into 10 power 5, and transition will happen from 3 into 10 power 5 to 5 into 10 power 5 Reynolds number. Then turbulent means Reynolds number greater than 5 into 10 power 5. And these are the Blasius solutions through which we can calculate boundary layer thickness, displacement thickness, and momentum thickness at the same time. Local skin friction coefficient also can be calculated separately for laminar and turbulent regions. So boundary layer thickness will depend upon REX. REX means the X depend X is the distance from the leading edge. So Reynolds number varies with the distance of the point, what distance the point is from the leading edge. Depending upon that, Reynolds number will be different. And once it is less than 3 into 10 power 5 means we will use these equations. And once the RE is greater than 5 into 10 power 5, we will use the turbulent equations. Okay. So delta is the boundary layer thickness, delta star is the displacement thickness, and theta is the momentum thickness, and CFX is the skin friction coefficient, local skin friction coefficient. Why local skin friction coefficient? Because it depends upon the X, and the distance varies, skin friction coefficient, and all these parameters varies. So these are the solutions or Blasius solutions, and using Blasius solution, we can calculate boundary layer thickness, displacement thickness, momentum thickness, and local skin friction coefficient for laminar and turbulent conditions over a flat plate. Okay, thank you.